Hey everybody, welcome to today's lecture for robotics. Today's lecture is on kinematics. And since it's on kinematics, I bet you're probably asking, well, what is kinematics? What is this lecture about? Well, the main thing is that robot arms are made up of joints, links, and tools. So basically you've got some robot arm, right? And you're trying to control it, sort of like the arm we've got in the corner over here. And when we're controlling this robot arm, when we're trying to do stuff with this arm, we know the joint angles, right? Because the robots have like sensors which are able to tell them what their own joint angles are. And we know the lengths of our links, right? Because that's based on the design of the robot. So the question that kinematics tries to answer is, where is the end effector? Where is this hand, right? Or the tool point? So we often draw these in these sort of simplified diagrams to represent a robot arm more simply than these complex pictures do. So to recap, forward kinematics is the problem of finding the end effector given the joint configurations. Okay, now we've got four common types of joints, which are revolute, and these are joints that rotate, right? So we can just picture them as being on a motor that can turn. You've got prismatic joints which can extend and retract, and that behaves as you'd expect it to. You've got a link that can get longer or shorter based on the state of the prismatic joint, and you've got screws and sphericals, but we're not gonna cover them in this lecture, but they exist. Okay, so we said robot arms are made up of joints, which are these things that can turn and move and whatever. Links, which are the sort of joining pieces, and the tool point, right? Sorry, I've got a bit of a flu, so that might happen a lot during this lecture. But so we've got this this arm over here, and where is the tool point? That's what we'd like to know, right? Commonly, when we're controlling a robot arm, what we want to do is get this tool point to pick up some object or manipulate some object, and to do that it needs to know how to get to that object or to that point, right? And if we have no way of telling where this tool point is, then we're not going to be able to control it. Okay, so let's figure out where the end effector is. So in this case, joint 1, which is this revolute joint, the base, right? So the base can rotate. But where it currently is at position 0, 0, 0. Okay. Then on the z-axis, we've got a distance of 3 to joint 2. So that means joint 2 is at 0, 0, 3. Right? We haven't moved in x, we haven't moved in y, but we have moved in z. Then, if we move along this axis, which we can see is actually x by 2, we'll get to joint 3. So that means joint 3 is at 2, 0, 3. And the tool point is 1 down in z, so it's 1 less in z, right? So the tool point is at 2, 0, 2. So if we sort of say relative to this axis, where's the tool point? It's currently at 2, 0, 2. So that wasn't too hard, right? We just moved along the axes and we got to the end. But what happens when the joint positions change? So this is a revolute joint, so it can rotate. This is a prismatic joint, so it can extend. And this is a revolute joint, so it can rotate as well. So let's say these joints are in a different state, right? So there's been some rotation here, and some extension here. Then where is the tool point? Well, now it's a little bit harder. So picture what happens from the top view when this joint rotates, when joint 1 rotates. This distance along x will no longer be along x, right? Because the system will have rotated, this link will actually be sort of maybe here or something, right? So it's no longer along the x-axis, and it makes it much harder to figure out where the end effector is, because we've now got a completely different bit of trigonometry to do. But let's see what happens. Let's picture a top view. If you were looking at this arm from the top and this joint rotated, right? you'd end up with something like this, where like initially you had your link going along the y-axis or x-axis or something, let's say the x-axis, and then when you rotate it, it was suddenly going along this sort of imaginary axis, and the parameter here would be how much you rotated, right? Now this picture should look a bit familiar to you from the lecture on coordinate frames. So that's what we do. We say, well, let's treat every joint and the end effector itself as coordinate frames. Okay, so that means we stick an axis on each joint. So we stick one there, we stick one there, we stick one there, we stick one there. Okay, there's going to be one more axis than the robot has joints, simply because there's one on the end effector, right, or the tool point. So when we treat these as coordinate frames, there's one easy question we can ask, is in reference frame 3, which is this one, where is the tool point? Well, it's at naught, 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 right? Because we specifically put it there. We put the reference frame on top of the joint, so we know that the tool point is at naught, naught, naught in this frame. Okay, but we only care about reference frame naught. So the cool thing is, what we can then do is find the transformation matrices that go from reference frame 3 to reference frame 2, and from reference frame 2 to reference frame 1, and from reference frame 1 to reference frame naught. Then we can take that position naught, naught, naught and multiply it by all of, pre-multiply it sort of by all of those transformation matrices, so that we get its coordinate in the world reference frame. I hope that makes a bit of sense. But the cool thing about doing it this way is that those transformation matrices can contain the states of the joints as parameters, which means that when the joint states change, we don't have to redo all our trigonometry or figure out the whole system again. We just plug in our parameters and away we go. If that didn't make too much sense, don't worry, we'll do some examples that'll make it a bit clearer. Okay, so does that mean the problem is solved? Well, no, not really, because this is still quite hard. So let's say I was trying to get from reference frame 3 to reference frame 2, right? Now the thing is, this joint rotates, right? And it could rotate in X, Y, or Z. I could also have a prismatic joint that translates along X, Y, or Z. In addition, this link could be weirdly shaped. As it stands, it's a straight link, but it doesn't have to be. It could go like down and then across and then down or something like that. It's not actually unusual in robot design that the link is not straight. Okay, so that means when I'm figuring out my transformation matrix from reference frame 3 to reference frame 2, I might have to rotate around X, rotate around Y, rotate around Z, translate along X, translate along Y, and translate along Z. So that's a lot of transformations I'm going to have to do. The other problem is that the order of these transformations is super important. So let's say I said I need to rotate around X, right? So I don't know if you can see my hand, but let's say my X-axis is my thumb and I'm rotating, right? That means my my Z-axis, which is sort of, let's say this was my Z-axis. If I rotate around X, my Z-axis is now in a completely different place. Okay, so if I said I needed to translate by 1 on the Z-axis, is it this Z-axis or this Z-axis? Well, it depends on when I do the translation, right? So the order is important. I must rotate and translate in the right order. And thinking about what order to what order to do this all in is actually quite difficult. So let's say I had this transformation matrix to get from 3 to 2, and it involved a rotation around Z and a translation along X and Y, and then another rotation around Y, and then a rotation around X, and then a translation along Y and Z. This would be my transformation matrix. I'd have to multiply all of these together, and that would just get me T3, 2. That would just get me from here to here. Okay, so the problem is I'd have to do so much thinking in terms of where all of these matrices should go, and that would just get me 1. I'd still have to then go and do the transformation from 2 to 1 and the one from 1 to 0. right? So that's just a nightmare. It's just too much to think about. So how do we defeat that? Well, the thing is, because we said we can rotate around any axis and translate along any axis and in any order, every transformation requires us to just think too much. Okay? So what we can do instead is we can make use of convention. Okay? And this means that we can make use of some rules that will make our lives easier. Okay? In particular, we have some conventions that say the joint effector operates in Z. So for instance, if we look at this this joint here, the rotation must be around the Z axis. In this case it is, so we're happy. Right. In this case, what I had previously was I had Z facing up here, right? Same as it is down here. But in order to obey this rule that the joint effector operates in Z, I need my Z to be pointing along this axis, because we said the joint operates in Z, and this joint, which is prismatic, extends or retracts in this Z axis. Okay? So similarly, this joint rotates around here, so that can't be Y, right? This thing going to the side is going to have to be Z, because it's the axis of actuation. But the other rule we have is that our axes are right-hand axes. What that means is that I take my right hand, right, and if I have my thumb pointing along Z, the curl of my fingers indicates a positive rotation. Okay, so if I look at the axis at the bottom, okay, I've got a Z pointing up and I've got an X pointing that way, so this way is a positive rotation. Does that make sense? Like, because my Z is pointing up, the curl sort of around the line is the positive rotation. And similarly, the positive rotation goes from X to Y, right? So if you look at this axis here and you try to follow the right hand axis rule, you'll see that if you point your fingers along X, it's a bit hard to do because the camera is upside down, if you know what I mean. Then if that's X, then I can curl by 90 degrees to Y, which is exactly what's happening in this axis, right? If this points to X, then another 90 degrees in the positive direction gets me to Y. Okay. Now here we've said that this axis is Z, right? So Z is pointing Z is pointing sort of, oh man, that way. This is so hard because the camera is not, so if this is X, then this would have to be Y, right? So in that case, if this is X, then this would have to be Y. Okay, Y would have to point the other way. The other thing I could do is I could say, well, let's let this be X, this downward axis, because then Y could be where it is, right? It's a 90 degrees positive rotation from X. Remember, where positive is the curl of your fingers on your right hand, if the thumb is pointing along the Z axis. So I'm going to do that. I'm going to let the X point downwards so that that's a valid axis. And similarly for this one, we've got our Z pointing sideways, that way. And if our Z is going to point that way, then if our X is up, then our Y needs to come out of the screen. Okay, so that's what we're going to do. Z points this way, so our X is up and our Y points out of the screen. And with the tool point, we don't really care about the orientation of the axes because there's no axis of actuation as it stands. So we can have our Z, X, and Y however we like, and what I'm going to do is make it the same as the previous one in order to avoid having to do any transformations because I am lazy. Okay, the problem is now when we look at it, there's a lot of rotations and translations to consider, right? There's rotations around X, Y, and Z everywhere. This Z axis is not aligned with this Z axis, so basically I'm going to have some transformation matrix that turns this z so that it aligns with this one, and turns this x so that it aligns with this one, and turns this y so it aligns with this one. Sorry, this flu is killing me. And a translation along the z-axis, and basically there's a whole bunch of annoying things to think about. But we can actually beat this by using something called the DENAVIT-HARTENBERG convention. Now, the intuition around why this works, why we can simplify this, is because I said there's like, a rotation around y, a rotation around z, a rotation around x, and there's a translation along x, translation along y, translation along z. But the reality is there's only one parameter, because any joint either rotates around a particular axis or extends or retracts along a particular axis, right? So there's only one parameter that defines what the transformation matrix should look like. So we should be able to represent our transformation matrix as A subscript I QI, where QI is the parameter for that joint. So meaning if that joint is at 40 degrees, then QI is 40 degrees. And AI is the transformation matrix, right? So AIQI would give us TI minus 1 TI. So for every joint, we can construct an AI with parameter Q that gives us the transformation matrix to the previous one, right? And then we can just chain these transformation matrices, so we can go from this one to this one to this one to this one. Same as we talked about at the end of the last lecture. Okay, now again, remember we said we normally need 6 variables, a rotation and a translation for each axis, right? But when we use the DENAVIT-HARTENBERG convention, we only need 4, okay? And our intuition around that is that if we introduce some restrictions around how we choose our axes, so remember here we said like this one could be x or this one could be x, it didn't really matter. That freedom is again a problem, because it makes it harder to, it means that the math is more complicated, right? If we reduce that freedom and we say let's introduce some restrictions around how we choose our axes, then we make the math a bit easier. And because it's a convention, like all conventions, it makes it easier to communicate around what our robot structure is, right? Now, the reason we can do this is because remember we said our joint either extends in one direction or rotates in one direction. Now, when a joint rotates, remember that means we're sort of rotating the plane. And when we're moving, we're sort of moving in that one axis, right? So that means the most that ever happens is that our joint is operating in one plane, okay? So if it's operating in one plane, it's not 3-dimensional anymore. The rotation is actually a 2-dimensional rotation. It's just, it looks like, we're operating on a 3D object, but it's only rotating in 2 of those dimensions, if you get what I mean. So because that's the case, we can pick which plane we're operating in, and we choose to operate in XZ, right? The plane XZ, which means we want to remove Y from our system. And how we do that is by introducing some rules. So remember, Z is the axis of actuation. That is exactly as it was before. The joint will either extend along Z or rotate around Z. Then we can choose our first set of axes, or first coordinate frame arbitrarily, right? This x0, y0, z0, it doesn't matter where we put x and y. Z of course has to be set because it's the axis of actuation, so this has to be z. But this could, for instance, be x, in which case y would go sort of pointing into the screen, right? So we choose our first axis sort of arbitrarily. In real life, you tend to align them to something useful so that you know what you're talking about in terms of x or y, but it's not pivotal that you do so. For the next reference frame then, reference frame 1, what we need to do is we need to say, first of all, xi must be normal, first z is the axis of actuation, so in that case this is our z. Then xi, so this is the x1 axis, must be normal to both zi and zi minus 1. So fundamentally what we're saying is it needs to be perpendicular to this z, right, and this z, okay, and it is, so we're fine. But if we look at how we had the axis previously, we had z here and we had x here, right? But the rule said that our x needs to be perpendicular to our current z and our previous z. But in this case, this x is not perpendicular to our current z. I mean to our previous z, right? So what that means is we have to shift it. So we're going to move our x to here because that'll make it perpendicular to this z and this z. Okay, so that was the first rule. So now you can see we got rid of our freedom. We couldn't just pick x here. We had to pick x here. And then by our right hand axis rule, this became y, right? This became y just because when you point your z like that, this is it's hard to do facing the camera, but do it with your own thumb. Point your thumb along zi and your fingers along xi, and then curl them 90 degrees and you'll get to y, right? It's not clear to me how to do that. Okay, this looks like it. So I've got my z along the axis that's in the picture and my x along the axis. So if I curl my fingers by 90 degrees, they end up pointing up to where this y is, right? This would be much easier in person. Sorry, I know this is a bit weird to try and follow. If there are any problems with how that arranges, please let me know in the Discord group. Okay, and then our third rule is that xi must intersect with zi minus 1. So x1 and z0 must intersect. So we can see that they do here. Okay, so that means we've obeyed all three rules, so we're happy. But have we obeyed all three rules over here? Well, so z is our axis of actuation. This is our x. Is it normal to my current z and my previous z? Yes, it is, right? It's perpendicular to this one and it's perpendicular to this one. Does xi intersect zi minus 1? Yes, it does. So x2 intersects z1. So we're fine. And, so on and so forth. Now, the cool thing about obeying this convention is it allows us to make the process algorithmic. We don't have to think about the order of multiplications anymore. We don't have to think about how our rotation matrix is going to look. What we do is we find some parameters that we use to construct our transformation matrix. So our DENAVIT HARTENBERG parameters are AI, which is the distance from zi minus 1 to zi along xi. So basically, it's if you take z naught. Okay, so let's take AI as the distance along x, right? So along xi, so in this case along this axis, to get our z's to meet, basically to get our origin to meet, right? And if we look at it, there is no movement along x to get our origins to meet. So in this case, our AI would be 0, but I mean, it could be non-zero in other cases. Alpha I is the angle around x that we need to rotate our previous axis to make it align with our current axis. So if we look at it here, our z is pointing up, right? Our previous z, and our current z is pointing out of the screen. So we need to rotate around this x to make this z align with this z, right? So meaning okay, so the axis we're rotating is this axis, but what we're rotating around is this x. Okay, so that's a bit confusing. We're not rotating around the axis's own x. We're rotating around the other axis's x, which is a little weird, but yeah. So basically what's happening is, I've got a z that's pointing up, right? My thumb is pointing along x1, right? So z0 is facing up. Oh boy, z0 is facing up. x1 is pointing to the right. So I want my z to be pointing where z1 is, like out of the screen. So what I need to do is I need to rotate by 90 degrees along around x, right? Does that make sense? So my alpha I would be 90 degrees. Di is the displacement along zi minus 1. So now look at this. This was along xi, meaning along the x-axis of my current reference frame. But when I talked about the displacement, suddenly it's along the previous reference frame. Okay, so that's quite a gotcha. It's something you're going to end up screwing up a lot unless you pay particular attention to it. So basically, when I talk about the displacement from xi minus 1 to xi, so along z, I'm saying what is this distance? So notice it's not along this z, it's along the previous z, right? So in this case the distance is 3, so di would be 3. And theta is the angle around zi minus 1 to go from xi minus 1 to xi. Okay, so in this case, if I look at this x and this x, now if I've got my z pointing up and my x pointing out of the screen, to get it to point to the right, I need to rotate by 90. Okay, so basically my theta I would be 90. But this joint can rotate. So if it rotated by another 10, then to make them align, I'd have to rotate by 100, right? So basically there's a variable here. Okay, but anyway, that's the DH parameters for joint I. Okay, so what I do is I make a table so I can get the DH parameters for every reference frame. Okay, so for reference frame 1, okay, see I have an error in the slide there because that shouldn't be minus 90, it should be 90. I'm just going to pause and fix that. Okay, so I've fixed that value. So basically if we look for our alpha, it's the angle from zi minus 1 to zi around xi, right? So we're rotating around x1 and we're trying to get z0 to be, we're trying to turn z0 to where z1 is, right? So we have our right hand axis and we have z pointing up. Oh boy, we have z pointing up and we want it to point out of the screen. I'm struggling to get this thing to align. Okay, so there we go. We have our z pointing up and our x pointing right, and we want our z to point out of the screen like it is in axis 1. So that's a 90-degree rotation. Okay, so that's why our alpha is 90. D, which is our displacement along z, is 3, right? That's the length of the link. And our theta is the angle around z to get the axes to align, right? Now we need 90 just to get the original position of x0 to be where x1 is. But then because we can rotate, when we rotate this, when we rotate joint 0, reference frame 0 won't move because it's sort of the world frame, right? It's where the axis is defined. But x1 will move because x1 is, because like if you picture the robot, when you rotate the space, then this arm is going to sort of swing, right? And z points along where this arm extends, so that means x is going to end up rotating as well, if that makes sense. So basically if you've got this sort of axis as it is now, if you've got this axis I don't know, this is hard to do because the camera is not facing the right, like it mirrors everything. So you've got this axis that looks like this, but if I rotate the bottom frame, then the whole thing rotates, so my axis is no longer where it's supposed to be, right? So if the joint rotates by q, by the value q1, then my theta will become 90 plus q1 because I'll need to rotate the 90 just to get the axis to align in the first place, and then by another q1 that accommodates for the rotation I just did. Okay, I hope that makes sense. And then if I look at the next joint, so from here to here, AI is the distance along XI, right? So this is XI. So based on this XI, what's the distance between this joint, between this reference frame and this reference frame, in this direction? 0, right? Because I mean, we don't actually move up, we move sort of across here. So AI is going to be 0. Alpha is the rotation around xi, this is xi, to get my z's to align, right? So again, I've got my x here, and my previous z is pointing out of the screen. And what my current z is doing is pointing to the right. So from here to here is a positive 90-degree rotation. It's a rotation that's going with the curl of my fingers, right? So that means alpha is 90. D, which is the distance along here, along z, right? So D is the distance along zi minus 1. This is zi minus 1. Is our parameter, is our joint parameter, right? This link can extend and retract because it's a prismatic joint. So the length of this link is our parameter Q2. So that means D is Q2. And our theta is the angle around zi minus 1. So this is zi minus 1 that gets my x's to align. So now in this case, xi minus 1 is this one and xi is this one. And I need to rotate around zi minus 1. So if you do that with your right hand, you'll see that that rotation is 90 degrees as well, right? This is the curve. If your thumb is pointing along this z, this rotation here from x1 to x2 is 90 degrees. Okay, so I filled in frame 2. For frame 3, the AI is the distance along xi, so this is xi. So what's the distance from this axis to this axis along xi? Well, it's 1, right? Because you can see there's a link of length 1 separating these two axes. And then other than that, these axes actually align. Okay, so let's do this. So alpha I is the angle around xi to make the z's align, right? But if we look at the z's, they're already aligned. So we don't have to do anything, right? Z is I mean, it's already aligned, so the rotation around x is 0. D is the distance along z, so the distance along zi minus 1, right? So this is zi minus 1. What's the distance between this axis and this axis? It's 0, right? Because the link is going along x, not z. So 0. And then theta I is the angle around zi minus 1 to get my x's to align. Now, that means it's the angle around this z to get this x to align with this x. But they're already aligned, right? They're pointing in the same direction. So, so that means the answer there is 0. But remember, this joint can rotate. And when it rotates, that means I will need to rotate around this axis around z to get it to align with this axis. So this is my joint parameter, right? Because you can picture that when I rotate here, that'll make this x. If I rotate around z, that'll make this x. Okay, so if this is my x, y, and z, if I rotate around this z, then x is suddenly going to be misaligned, right? It's gonna it's gonna turn, and so I'm going to need to turn the next axis in order. I'm going to have to turn the previous axis in order to align it. So there's a joint parameter here. So if it's 0, fine, then this is 0 and there's no problem, but it might be Q3 if I rotate. Now all of that was pretty hard, so you may be thinking, well, why did I do all that? Well, first of all, the point was it was algorithmic. I could do it without really thinking. Yes, there was calculation involved, but there wasn't reasoning, right? Like, I didn't really have to kind of figure out stuff. I just had to follow the rules, which is a lot easier. And when I've got these parameters, the really cool thing is I can frame my transformation matrix as a rotation around x, a shift in x, a shift in z, and a rotation around z. Okay, in that order. So what the DENAVIT-HARTENBERG convention allowed us to do is now we don't have to think about the order of these things. We don't have to think about how any of this works. Basically, you know, whenever we have an arm, regardless of what the arm looks like, we do exactly the same operation, right? We figure out the DENAVIT-HARTENBERG parameters, and then we've got this this transformation configuration basically. And this allows us to create a transformation matrix, AI, right? We said it's a rotation around Z, a rotation around X, a translation along X, a translation along Z, and a rotation around Z. Remember, we pre-multiply, so the order is in the opposite direction. But when we do that, that means our AI is equal to our rotation around Z. Remember, we know what that looks like. Our translation along Z, we know what that looks like. Our translation along X, we know what that looks like, and our rotation around X, which we also know what these look like. These come directly from the last lecture, but they're sort of known matrices, right? And our AI can then be just the multiplication of these. So we get that AI is equal to this beast. Okay, I've changed the notation a bit. So this is cos theta I, this is sine theta I, this is cos alpha I, just to make it easier to read. And the cool thing is that AI is then the transformation matrix from reference frame I to reference frame I minus 1, right? But where this is really powerful is that this is always AI, right? AI is always equal to this matrix. No matter what arm I'm working on, no matter what its joint configurations are, this is always the transformation matrix. So that means I don't have to figure anything out anymore. If I figure out the DENAVIT HARTENBERG parameters, I can just plug them into this, right? There's a theta, an alpha, and a and a d, and I just plug them in from my table, and I've got the transformation matrix. So as it stands, that means I'm going to have 3 transformation matrices, A1, A2, and A3, and those will accomplish the transformation for this arm. So that's pretty cool, right? Like I just plug in my 0, my 90, my 3, and my 90 plus Q1 into here, and I've got A1. Now, so here we spend a lot of time, talking about how this works and the derivation, all that. Well, a little bit of the derivation. The plus side is that in general, you fundamentally just have to have access to this matrix. Either you're memorizing it or you're looking it up somewhere. And then you just work out the DENAVIT HARTENBERG parameters for your arm, whatever arm it is. You plug it in and you get your transformation matrix. So this, next week, Monday, we'll be having a TUT that will give you some examples some exercises to work through to actually produce these transformation matrices. So I realized that was a lot. I hope that it may take repeated viewings, and of course, always feel free to look for other online lectures and any other PDFs or material that you want to look at to sort of get your understanding to where it should be. But hopefully the lecture gave you a decent introduction to kinematics and how it works, and the TUTs will get you doing the calculations. Thanks everybody for listening. Enjoy your day.